So in this chapter, we are going to talk about acids and bases, all the different kinds that there are. First of all, just a little review on the different kind of arrows that we have in organic chemistry. So the first one is just the synthesis, which is the yield arrow going in one direction. The other kind is equilibrium, where you have reactants and products that are in equilibrium with each other, which means they're going back and forth, and you can push the equilibrium forward or reverse. The third kind of arrow is the resonance arrow, double-headed arrow, and in this case there is no starting material or product and there is no equilibrium going on. It is a resonance, which means there's transfer of electrons going on. Retrosynthesis is a backward synthesis, which means that you start with your final product and end up with the starting material. So we will do this one later on. In this chapter, in this topic, in acid base, this is the arrow we're going to use a lot, which is the transfer of 2 electrons. And this is called a curved arrow and a double-headed arrow showing a transfer of 2 electrons. This curved arrow down here with just one head is the transfer of 1 electron. We will use this one the most in this chapter. So let's talk about acids and bases. The first theory of acids and bases was the Arrhenius theory, which states that acids are proton donors, whereas bases are hydroxide donors. That got changed and revised, and eventually we came out with the Bronsted-Lowry theory. And the Bronsted-Lowry theory states that a Bronsted acid is something that donates protons, whereas a Bronsted base accepts the protons. Again, remember, a proton is H+, and that is because a hydrogen atom has only an electron and a proton, and once the electron is gone, the only thing that is remaining is a proton, which is just a particle. Okay, and so that's why it's called the proton. Here, this is an example of a typical acid-base reaction, of HCl as an acid, which would be a proton donor. Water is a typical base here, and it's a proton acceptor. And what's going on over here is that the acid is giving its proton to the water. Okay, and see the transfer going on here. And so now finally in the products, the water has accepted the proton and became hydronium ion. The acid lost its proton and became chloride ion. The water goes from being H2O to H3O+, which is the conjugate acid then. The hydrochloric acid was HCl and it went to Cl-, which is the conjugate base of HCl. Here are some real examples, a little bit more concrete example. Here is an acid. Now water is the acid. Remember, water can be an acid or a base depending on what it is reacting with, and those substances are called amphoteric substances. So water is an amphoteric substance. So here water is reacting as an acid, whereas NH2- is the base here. NH2- is what is picking up the proton here. Now these arrows, these curved arrows here, these are what we use to show transfer of electrons going up. So nitrogen here is picking up a proton, and remember, when a proton is being picked, proton means no electrons. So it picks up H+, which means the H+ will go to the NH2-, which becomes NH3 then. Whereas the proton, when it leaves its electrons on the oxygen. Okay, remember, proton leaves without its electrons. And so those electrons are being left on the oxygen, and that becomes then the hydroxide. Because the water, which is the acid, has lost the proton, it became the conjugate base. The base here, NH2-, it gained a proton, and so it became the conjugate acid. The second reaction here is between HCl, which is your typical acid, and then a base, which is methanol. This reaction is very similar to what is here also between water and acid. In this case, in case of methanol, there's a CH3 here. In case of water, there was just a hydrogen here. So now the methanol is picking up the hydrogen, becoming CH3OH2+, whereas the acid is giving the proton, and once it gave the proton away, it became Cl-, which is the conjugate base. Now remember here, since the oxygen is picking up a proton, H+, you have to add the H+. Okay, and since oxygen is starting the reaction, the H+ is adding to the oxygen. Oxygen here has 3 bonds, and so it gets 1 positive charge. That's the formal charge on it. This is called the oxonium ion. And that's the conjugate acid. Okay, so this is your typical acid-base reaction, and these red arrows, these are the electron transfers that are going on in this reaction. There is a rule for forming conjugate acids and bases, and that is when you have a strong acid, it ends up giving a weak conjugate base. And this is a very important fact for organic chemistry. This is possibly one of the most important fundamental topics in organic chemistry, understanding acids and bases. So if you did not understand that in Gen Chem, understand it now, because it's going to stay with you for Organic Chemistry 1 and Organic Chemistry 2. So a strong acid will give a weak conjugate base. A weak acid will give a strong conjugate base. A strong base will give a weak conjugate acid. A weak base will give a strong conjugate acid. Okay, and that's how it occurs. And this is the rule, this is how it happens. So here we have HCl, as in the previous reaction. HCl, which is hydrochloric acid, is a strong acid, so it ends up giving a weak base. Okay, so that's the conjugate base. Water, which is really quite a weak base, it's kind of amphoteric, it can be acidic or basic. And so water is a weak base, and in front of hydrochloric acid, this is the base. And so this is a weak base, and this weak base becomes comparatively a stronger acid now. Okay, and this is the conjugate acid here. In this case, where we have acetic acid and ammonia, acetic acid is an okay acid. Okay, it's not very, very strong. So it gives a nice strong conjugate base. Ammonia, which is a weak base, will give a strong conjugate acid. Remember, acids are always going to be more positive and bases are going to be the negatives. Okay, bases have more electrons in them. Okay, whereas the acids, they have protons in them. So whether you have acid on the left hand side or on the right hand side, the acids are always going to be positive because they have that extra hydrogen in them. Okay, so HCl was the acid here, and hydronium ion is the acid over here. It's the conjugate acid. Same thing here. Acetic acid, which is a proton donor here, is now become the conjugate base, but ammonia now picked up the proton, so this became the conjugate acid, which has the extra proton. I just want to make a little note over here about the arrows. If you look at the arrows here, this arrow is a straight arrow, which tells you that you're reacting a strong acid and fairly strong base. Not fairly strong base, but in front of the HCl, this is a good base. And in this case, this is an equilibrium arrow because both of these are weak. Okay, and so we use equilibrium arrow. Again, this is not such a big point, but just to make a note of it. Here are some examples of acids and bases. It's a good idea to keep this table handy so you have a good understanding of what these acids are. All acids and bases can be divided into two, organic and inorganic. Inorganic are very easy, as you have seen them before. Hydrochloric acid, sulfuric acid, water, nitric acid, phosphoric acid. Those are the inorganic. These are also called the mineral acids. Organic acids, the one that you are most familiar with is the acetic acid, which is the common vinegar. Citric acid is the one that you drink all the time in the juices. For bases, the inorganic bases are pretty much all hydroxides. There are no hydroxides given here. Well, there's a hydroxide given here, but there's a counter ion. So whether it's sodium hydroxide, potassium hydroxide, calcium hydroxide, whatever it might be, all hydroxides are going to be bases. Ammonia is a good base. Ammonium hydroxide is a good base. Amides are bases. And then some carbonates and hydrogen carbonates are good bases. So for example, sodium carbonate, sodium hydrogen carbonate, those are considered to be good bases. Organic bases are varied, okay, and so here is some amines, methoxides, and as we go on, we will learn more about these bases because organic bases are quite different than organic acids, and you may not have encountered them so much in general chemistry, so you will see them a lot more now, okay, than you did before. Okay, so let us work on some solved problems over here. And let's take the first one. What is the conjugate acid of NH3 ammonia? Without looking at the answers, you look at the compound that's given to you. You see it is NH3, and since you're being asked what is the conjugate acid, you add H plus to the NH3. So adding H plus literally would give you NH4 plus, and that's what the answer is. The next question. Question 2, what are the conjugate bases in the reaction below? So you have carbonate and hydrogen sulfate ion to give hydrogen carbonate ion and sulfate ion. So here's what's going on. The carbonate ion does not have the proton here, but the hydrogen sulfate does. And in the products, you can see that the carbonate has accepted the hydrogen or the proton, okay? So looking at the bases, you would need to have something that does not have the protons, which means the carbonate and the sulfate. So those would be the conjugate bases. So the answer is E, where you have the carbonate and the sulfate. The HSO4 minus and the HCO3, the hydrogen sulfate and hydrogen carbonate, these two are actually going to be conjugate acids, okay, in this reaction, because those two have the protons in them. Okay, so next reaction then, next problem. In the reaction below, which are both acids in this case. So now you're looking for extra protons on both sides. So this is CH3 NH3 plus, this is water. On the right side, CH3 NH2, you can see that the CH3 NH3 plus has lost a proton, which means this must be the acid. So if it's lost a proton, this is the conjugate base. And since water has gained the proton, now this one is the conjugate acid. So your acids are positive species, and right here, okay, these are your positive species. So these two are the acids, so D is the right answer. A strong acid leads to a weak conjugate base. Okay, so here's just some solved problems. These are the problems, or these kind of the problems that you're expected to solve as far as acids bases are concerned right now. There might be some organic ones too. These are inorganic. The CH3 and H3, this is organic base. So this one you should know, and these are all mineral ones. So this one you've seen before, hopefully. Now for the acid strength and pKa, one of the most important things for any acid-base reaction is why does an acid-base reaction take place in the first place? Okay, and so an acid-base reaction takes place because it leads to more stable products, okay, whatever they are, conjugate acid and bases. And really for an acid-base reaction, the important thing is that the conjugate acid and the conjugate base that are produced will be weaker conjugate acids and weaker conjugate bases than the starting material. That is what the driving force of the reaction is. And so that's how we know that an acid-base reaction is taking place, all right? So again, an acid-base reaction takes place only when the products are weaker conjugate acid and a weaker conjugate base. So which means to predict whether a reaction is actually going to take place or not, we need to know whether an acid is strong or not, and whether a base is strong or not. I stick with one thing usually, the acid strength. The base strength kind of follows it. Okay, so we'll talk about that. But anyhow, for now, let's talk about the acid strength, and that is related to pKa. So in any case, for now, the strength of an acid is determined by the ability for an acid to donate a proton. So the more it can donate a proton, the stronger acid it is. Okay, and remember from your Gen Chem that pH is negative log of hydronium ions, so which means that the more hydronium ion there is in solution, the stronger the acid is going to be. pH works great when you have strong acids and strong bases, but you can take the pH of weaker acids and weaker bases also, and it's the hydronium ion concentration is calculated just a little bit differently for weaker acids and bases because there is an equilibrium involved. And when you have an equilibrium, you have to take the equilibrium constant. Okay, and so this is what the reaction is, and this is something you've done in Gen Chem 2 in great detail, how to calculate pKa of weak acids and weak bases. So this is what the equation is, and so that's how you get the Ka. And K equilibrium is just for any random equilibrium. However, Ka is for any equilibrium that is involving an acid. So that's what this is. So again, if you see, the hydronium ion is on the top here, so which means that the more hydronium ion you have, the higher the Ka would be. Now, Ka would come out to be a number, of course, but it will usually be like times to the negative 10 to the negative 5 or negative 6, which means it's an exponent form. And sometimes those are a little bit harder to remember. So what we do is, and we take out, we calculate the pKa of it. Okay, and pKa is like the pH, which means negative log of the Ka. And this gives it a little bit more of a measurable number, or a number that you can remember, or at least if not remember, at least it's not an exponent form. So pK values are more common for us. We'll talk about the strength of acids and bases as we go on. Here is a nice table, and you may want to print this out, and I can give this to you in class as well if you want. But this is really one of the best tables that I have found for pKa. And the way it works is that here are your acids. This is the strongest acid. And remember, a strong acid gives you a weak conjugate base. All right, so the acids are on the left-hand side, and on the right-hand side is the conjugate base. Okay, so a strong acid gives you a weak conjugate base. A weak acid will give you a strong conjugate base. So if the strong acid is over here, the strong base is down over here. Okay, because strong acid gives you weak conjugate base. These are pKa values, and as you can see, these pKa values are not in exponent form anymore because you've taken the logarithm of this, of the Ka. So pKa values go from negative to positive. The more negative the number, the stronger the acid. That's how it goes. So the lower numbers are stronger acids, the higher numbers are weaker acids. This table is really quite good because it gives you a variety of acids in here. You can compare inorganic acids to organic acids, to bases, and some of the simple hydrocarbons. So it's a really good table to keep handy. You cannot use it on the exam, but if you look at it long enough, then hopefully you'll remember some of the placements. Okay, so for example, hydrogen iodide is very strong acid, sulfuric acid, very strong acid. Hydrochloric acid is also right up there as far as the strength is concerned. Hydronium ion right here, okay, in the middle. Hydronium ion is not a very strong acid, but fairly there, okay. And then acetic acid, which you're familiar with, is right here. Again, you might remember the pKa value from doing all your calculations in Gen Chem 2. So acetic acid, not very strong acid, so it's kind of getting into the middle now. Ammonium ion, this one is phenol. We'll encounter this later on in organic. Water is down here. Water, of course, not an acid. Okay, it's not even a base for that matter. It's an amphoteric substance. And then going down here, you can see that now we are getting into hydrocarbons, which is the CHs and the CHs. Hydrogen, which is not even considered to be an acid. So obviously this is going to be very, very weak acid, which means it gives a very strong conjugate base. And the same thing goes for these compounds over here, which are not even considered to be an acid because they don't have any protons to give. And so they have very strong conjugate bases. So again, just look at this table and don't try and memorize it, but at least see the placements. Okay, the more you look at it, the more you will remember some of these things. Okay, so here are some factors that actually determine acid strength. This is something that you do have to remember, so please understand this carefully. This will be useful for you in Organic 1 and Organic 2. Okay, so the factors that are important for us are electronegativity, which is across the row, which means as we go across the table, then electronegativity increases. and we'll talk about how that affects the acid strength. The size of the anion, so now we're going to go down the group. Instead of across, we're going down the group. We'll talk about halogens over here and some more examples. The number of oxygens, so for example here HNO2 versus HNO3, nitrous acids versus nitric acid, okay, which one is better acid? Inductive effects, and we'll talk about what inductive effect is. Again, this is a very important concept in organic chemistry. Resonance stabilization, we have already talked about resonance, so you know that it's a movement of electrons. So how does that affect acidity? We'll talk about that. Acidity of hydrocarbons. Now, if you remember from the previous slide, that hydrocarbons are not really very good acids, but still some of them are okay acids. Okay, so they're not extremely strong, but in their own terms they are acids. And then the solvent effect, okay, and so which means that if you have polar solvents versus non-polar solvents, okay, then which one is going to be a stronger acid? So we'll take all of these one by one and discuss the strengths, okay, and see how what makes a strong acid. And remember, this is only talking about the acid strength, and now you understand why I talk only about the acid strength, because the basic strength is the opposite of acid. So when you have a strong acid, obviously you have a weak base. So the first one, electronegativity in a row, okay, so which means you're going across the periodic table. So here is how the electronegativity increases, okay, and so here are some examples of the compounds which are in this row. So starting with CH4, which is methane, going on to ammonia, to water, and then HF. And look at the pKa, all right, how dramatically it's changing. So by the time we get to HF, or hydrofluoric acid, the pK is really low, okay, and that's because electronegativity is really high here, which means that this bond is extremely polar, and if this bond is extremely polar, it is easy for this hydrogen to go away. Essentially, if you can remember that concept, then it's very easy to understand acid bases. Okay, so the more polar the bond is, the easier it is for the hydrogen to go away or a proton to go away, which makes it a strong acid. Okay, so here are your strong acids on this side. So which means that the basicity is opposite. Okay, so if this is a weak acid, it's got to give you the strongest conjugate base. Okay, here are some more examples for acids and then the conjugate base. Okay, so this is for oxygen, nitrogen, and carbon. Yet again, a little bit different than what we have in this category. So let's talk about this concept of size of anion. Okay, and so now we are going within a column, and we're going to go down a column, all right, and see how that affects the strength of the acid. So as we go down a column, the atomic size increases, okay, and the anion also, of course, increases. As the anion increases, its ability to bear the charge, the negative charge, is more, and therefore it becomes more stable. Why is the ability more? Because it already has more electrons, so heck, it can take one more, and so therefore it's able to bear it a little bit more. So here is an example of the halogens, okay, and so hydrofluoric acid, hydrochloric acid, hydrobromic, and hydroiodic acid. Hydroiodic acid is one of the strongest acids in this case because the iodide ion can really take that extra negative in it, because it's a huge anion, it's a huge atom also. HF, on the other hand, the fluoride ion, is a very small ion. It cannot really hold on to the negative charge, even though it's very electronegative, but the size is very small. And therefore it's not such a strong acid compared to HI. Okay, within the same group, the hydroiodic acid is the strongest acid. One of the other ways of looking at this is that the iodide atom is so huge in size that it really cannot hold on to the hydrogen, and because of that reason the hydrogen is ionized. Okay, it's in the solution. On the other hand, in case of HF, these two atoms are almost the same size, which means that the bonding, the overlap, is very good. And if the bonding is very good, then the hydrogen is not going to want to be in the solution. So that's another way of looking at how size affects the pKa. Another example here is for group number 6, where you have oxygen, sulfur, and selenium. Again, one might think that water is going to be the strongest acid because oxygen is the most electronegative, but it's not about the oxygen so much as it is about the size of the atom. So selenium here is the biggest size, and because of that, it can hold on to the electrons a little bit more, and therefore it has the smallest pKa, hence the strongest acid. Okay. Now going to the number of oxygen atoms and electronegativity. This is kind of related more to electronegativity than anything else. And this also brings up another point that I wanted to mention before, is that in recognizing what is a good acid, okay, or what is a good proton, I should say, because acids donate protons. Usually the proton that is dissociating is bonded to the oxygen. Oxygen and hydrogen bond is a very polar bond, okay, and because of that reason, the hydrogen that is attached to the oxygen is the one that's going to ionize. And if you look at the Lewis structure of any acid, like phosphoric acid, sulfuric acid, hypochlorous acid, all of those, you will see that the hydrogen that is dissociating is attached to oxygen, okay? So here are two examples, one phosphoric acid and one for phosphorus acid. Now, both of them almost are the same, except one has 3 oxygens, one has 4 oxygens. And so in this case, which is phosphoric acid, H3PO4, phosphoric acid is a stronger acid, phosphorus acid is a weaker acid. And phosphoric acid is a triprotic acid, whereas phosphorus acid, even though it has 3 hydrogens, is a diprotic acid. So the triprotic acid from H3PO4, phosphoric acid, is coming from the fact that the 3 hydrogens are attached to the oxygen. The diprotic acid in phosphorus acid, even though it has 3 protons, is coming from the fact that only 2 of the hydrogens are attached to the oxygen. The third hydrogen is actually bonded to phosphorus, which is not such a polar bond. This bond between hydrogen and oxygen is more polar. So therefore, this phosphorus acid becomes a diprotic acid and not a triprotic acid. This is the same reason why nitric acid is stronger than nitrous acid and sulfuric acid is stronger than sulfurous acid. Here nitric acid has 3 oxygens, nitrous acid has 2 oxygen, gives it more polarity. And here also sulfuric acid has more oxygens than sulfurous acid, giving it more polarity. If you see, that's the same case here also. Phosphoric acid has 1 more oxygen, which also gives it more electronegativity and more polarity. For organic acids, acetic acid is going to be stronger than methanol, or carboxylic acids are going to be stronger than alcohols because carboxylic acids have 2 oxygens, whereas alcohols have only 1 oxygen. Because of that, this proton is ionized, and it's more ionizable than this proton. When I was talking about before that the proton that dissociates is bonded to the oxygen, this is what I'm referring to. There is these protons over here which are bonded to carbon, and this proton here which is bonded to oxygen. This proton is the one that is the acidic proton. This one is not acidic. Same thing over here with alcohol. This proton is the acidic one, whereas this one is not acidic because it's bonded to carbon, and that bond is not very polar. Inductive effect is a very simple concept, and the concept here is that if you have an electronegative element, it will pull electrons, and that pull is going to be felt over 2 or 3 bonds, but not more than that. Okay, just 2 or 3 bonds, that's it. So which means that if you have, say, fluorine attached to a CH2, CH3CH2, that pull of fluorine is felt also on the second bond, not just on the first bond, but also on the second bond. So what this does, it makes this bond also a little bit polar, even though there is no fluorine attached here, but the effect of fluorine is also on this bond. Okay, and so this is called inductive effect. Inductive effect is both kind, which means that if you have an electronegative element, it pulls electrons towards itself. On the other hand, electronegative effect can be the other way, which means that some elements can push electrons into the compound, okay, rather than taking it out. In this case, we're talking more about pulling electrons because that weakens the H bond, okay, or the OH bond. So here again is acetic acid and ethanol, and you will see how the number of oxygens affect acetic acid. So it's not just because you have the more oxygens in there, you also have inductive effect working for you. So here is oxygen which is pulling electrons, here is oxygen which is pulling electrons, which means you have this whole pull going on, and what this pull does is it makes this hydrogen more ionizable, okay, which means that it is easily given off. That pull is not so much in this case where you have ethanol because there's only one pull right here. Whereas in acetic acid, there are actually two oxygens that are pulling on this hydrogen. So it weakens this bond. So you can see the same effect if you have something like ethanol and then something like ethanol, in which case all the hydrogens are replaced by fluorines here. So now this hydrogen, in case of simple ethanol, is not so strong of an acid, but when there are three fluorines in place of the hydrogens, now you have the inductive effect working for you, and so this hydrogen is going to be more ionizable, and therefore the pKa of this acid is smaller, so which means that this is the stronger acid. And here are some comparisons for this acid where the chlorine, where you start with no chlorine on butanoic acid, one chlorine at the end, and then the chlorine moves closer, and then the chlorine moves even closer to the ionizable hydrogen. And then you can see the change in the pKa. By the time the chlorine is the closest to the H over here, it's a nice strong acid. Okay, so that's how inductive effect works. Resonance. This one is an interesting one also because in this case, when something is more resonance stabilized, then it wants to stay that way. Okay, so what we talked about resonance before, it's an important concept. Okay, and so if something is resonance stabilized, it will want to stay in that ionized state. So for example, now we'll compare alcohol and acid again. Now you can see that we're getting more and more into organic bases, okay, and organic acids. And so here we have alcohol again, and alcohol is giving the proton, so which means that's the acid, and this is the ion we get, okay, from the alcohol. And then here is carboxylic acid. Carboxylic acid is the acid here, it gives the proton and it gives this ion, which is the acetate ion. This acetate ion can form a resonance structure. So here's the movement of electrons from the oxide ion to this bond, and then this double bond to the oxygen like we did before with the carbonate ion. And this is the resonance structure you get. See the resonance arrow over here. This is equilibrium arrow and this is the resonance arrow. And so these two structures are in resonance, okay, with each other, which means that they are stabilized. They're equally contributing and they are stabilized. If this is stabilized, then the hydronium ion is not going to be bonding right back over here to give the acid, which means that this reaction is shifting more forward than backward. In the case of alcohol, you form the alkoxide. There is no place over here for these electrons to resonate. Okay, so there is no movement. If there is no movement, there is no resonance structure, which means that once you form this, it's easy for this ion to pick up the hydrogen right back, to pick up the proton back here, and go right back to the alcohol. So for that reason, alcohols are not very good acids. Okay, and so look at the pKa of this one. The pKa of this alcohol is 15.9, whereas the pKa of acetic acid is 4.76. That is how much effect the resonance has. Now, as we are going through all of this, you have seen that there are 2 or 3 factors that make acetic acid a strong acid. One was the number of oxygens that were in it, and the second one was inductive effect, and the inductive effect is because of the oxygens in there, and now resonance also, so which makes these acids fairly good acids. Now let's look at hybridization. This is a simple concept again. The more the S character there is in the hybrid orbital, the more acidic it will be, okay? And so we learned three different kinds of hybridization: sp, sp2, sp3. In case of sp, you have a 50-50 character of S and P. In case of sp3, the S character is only 25%, which means that the sp hybridization is the most acidic one. So the sp hybridization is more in these cases, which is alkynes, and alkenes are sp2 hybridized, alkenes are sp3 hybridized. All right, so the alkynes are the most acidic and the alkanes are the least acidic, okay, of all the hydrocarbons that we're talking about. And here are their pKa's. Now remember, if this is the strongest acid, it will be the weakest base, okay, conjugate base. This is the weakest acid, hence it gives the strongest conjugate base. Here are the pKs again, so you can look at them. You don't have to memorize anything, just remember the trend. The last thing here is the effect of solvent. Any solvent that supports ionizations, which means a polar solvent, that will give you more acidity, okay? And so usually in gases, you don't really get very good pKa's because the ions are not stabilized very well. But as soon as you put them in water, things are now polar, and because of that, the ions are stabilized a lot more. So if you have more polar solvents, you have better acid-base reactions. If you have a non-polar solvent, then the acid-base reactions are not going to be very good, okay, because the ions are not supported very well in those kind of solvents. So a good polar solvent would be water, for example, methanol, alcohols. Those are good solvents. Something with zero dipole moment like benzene, hexane, those are not considered to be very good polar solvents. Those are non-polar solvents, so they will not support the acid-base reaction that much. That is the effect of solvent. The strength of bases. As I said to you, bases are completely opposites of acids. And so whenever you think about what makes an acid a strong acid, just do that first and then figure out which is the strongest base. Okay, so for example, when we talked about hybridizations, we said that sp3 are the weakest acids, which means they give the strongest conjugate base. Okay, the same thing goes with inductive effect, same thing goes for resonance, everything like that. Okay, and so it's the same kind of philosophy. I usually just work on my acids first and then figure out the bases. So even if I have bases, I will convert the base into the conjugate acid and then see which one is the stronger acid or base. That's the best way to do bases. Try not to remember both the strength of acids and bases separately, otherwise it will be too much to remember. Okay, so best remember your acidity rules, and that's how you figure out whether you have a strong base or not, because it's completely opposite of it. Now, for one of the last categories of acids and bases is the Lewis acids and bases. You did this back in Gen Chem also, Gen Chem 2. So if you want to review there also, you can, but here is a small review. Lewis acids are species that will accept a pair of electrons. Lewis bases will donate a pair of electrons, okay? So it's actually a transfer of a pair of electrons, okay, between acid and base. There is no pKa scale for these acids and bases because there is no proton donation going on. And so you cannot calculate how many electrons are in solution and so on. So there is no pKa scale for this. Their effectiveness is measured only by how well they can donate or accept an electron. Sometimes they're slightly better than the others just because they are more in need of an electron or more capable of giving an electron. Examples of Lewis acids are group 3 elements. Group 3 elements, BF3, if you can remember, was one that had an incomplete valence shell after bonding, also incomplete octet, and because of that, it can still accept a pair of electrons. AlCl3 aluminum chloride is the same way, okay, because they have incomplete valence shell, they can still take 2 more electrons. Transition metals are also very good acceptors of electrons, again because they have the d electron orbitals, and therefore they have some more room in there and they can accept electrons. In case of organic compounds, what we will deal with is carbocation, that is a carbon with a positive charge. And again, since it's a cation, it can accept a pair of electrons. Okay, so those are going to be your Lewis acids, and that's the best way to recognize them. Okay, which means group 3, metal cations, and then carbocations. Those will be your Lewis bases are many, and especially in case of organic compounds, there are many Lewis bases. Lewis bases is anything that will give a lone pair of electrons. So literally wherever you have an oxygen or a nitrogen, that's where you have a Lewis base. So all of these different functional groups that I have given over here, these all can be Lewis bases. So look at the oxygen in all of these, and these can be Lewis bases. So you can write a reaction of all of these. We will talk about functional groups very soon, so you don't have to memorize all of these right now. What I want you to focus on is more that oxygen has the electrons to give. I need you to focus on the atom that is capable of giving an electron. So here we have an alcohol. Okay, this is the first example right here. An alcohol, which is the base, and here is an acid, and these electrons are being donated over here. Okay, and so this gives you now the conjugate acid. Okay, so that's an electron pair donation going on. So this is your base. Okay, here's an ether, same thing. Okay, this is an ether. Ether is has oxygen with 2 lone pair of electrons, again giving its electrons. Here is a ketone. Ketone is right here, again lone pair of electrons giving its electrons right here. Okay, if you notice here, these acids, these are all typical acids. Typical meaning Bronsted acids, which means they donate proton, but the bases here are what we call the Lewis bases. Okay, they can accept a proton, yes, but they are donating electrons over here. So let's look at some solved problems. Which of the following are Lewis bases? The simplest thing here to look for in a Lewis base is the fact that it should have a negative charge or it should have lone pair of electrons. So amongst all of these species here, go back, right here. This is the negative species, and so this one is the Lewis base. All the other ones, BCl3, remember this is group number 3, and all of the other ones are positives. So these are actually all Lewis acids then. Second question, iodine trichloride will react with the chloride ion to form ICl4-. Which species is the Lewis base? Which means, is it this one, is it the chloride ion, or is it this one? Okay, not this, the ICl3 or the chloride ion. In these two cases, ICl3 or chloride ion, again, it's going to be the -1. Okay, that's going to be the Lewis base because it has extra electrons in there. Third question, which one of the following is a Lewis acid but not a Bronsted-Lowry acid? Remember, Bronsted-Lowry acid is a proton donor, which means that you'll have a hydrogen in there. Iron 3+, hydronium ion, HSO4-, NH3+. These all have hydrogens in them, so these all can be Bronsted-Lowry acid, which leaves only iron 3+ as our Lewis acid. Which of the following species will act as a Lewis acid? NH3+, not so, because that donates a pair of electron. NH4+, no, because it gives a proton. This is actually a conjugate acid. H2O, no, this is a very good base. BF3, yes, this is a good acid because this is group 3. F-, no, because this is negative. Here are some Lewis acid-base reactions, and you need to kind of know them because you will be given these. And in these cases, your acid and base, most of them are not your typical acid base. Okay, so for example, if you look at this one, there is no proton donation or anything going on. Here also there is no proton. So you really have to look at what is the electron-rich species and what is the electron-poor species. So here I've given you some clues to look at. So for example, the electron-poor sites are going to be the cations, and these are going to be also your Lewis acids. Okay, electron-rich rich sites are the anions, and those are the ones that are going to be Lewis bases. Okay, so here, this is the cation, this is the Lewis acid. This is the anion, so this is the Lewis base. The Lewis base gives electrons to the cation over here, and here's the new bond that's formed. In Lewis acid-base reaction, there is no water formed, okay, because there is no protons over here. So, and there are no hydronium ions, so you don't really see any water forming, okay, in these cases. Here is another typical Lewis acid-base reaction where you have ether. So these are the electron-rich species. And here you have BF3, which, as we talked about, is a Lewis acid. This is the electron-poor species. It can take a lone pair of electrons. So the lone pair of electron is transferred from oxygen to boron. Here is the new bond formed. And remember, oxygen gave electrons, so it became positive. Boron accepted the electron, so it became negative. Again, this is a weird looking complex, but that's what you form in Lewis acids and bases. This is the salt, okay, that you form. So there is a positive and negative right there in the same compound. Some Lewis bases also have double bonds in them. Okay, so this one that I chose to show you here is a double bond. So there is no lone pair of electrons, or there's no electron poor species. It's actually electron rich by the means of a double bond. So the double bond here goes for the proton, and this is what we end up getting. Now remember, this one here becomes an acid. This was a base, it becomes an acid here. This was an acid, this becomes the conjugate base. Okay, so that's how the Lewis acid base reactions work. Here are some of the common acid-base reactions. Just go over them and see if you can follow through with the mechanisms. Okay, the most important thing is that your arrows will always start from the base, and they will always go towards the proton, or they will go towards the positive side, as they did in the Lewis acids and base reactions. Okay, so that's what I want you to focus on in all of these three reactions. So copy these, write them on your own, and then you can check your answer over here. Okay, so the first one here, amide ion, picking up a proton from here, electrons being transferred to the oxygen, so you end up getting hydroxide, and the NH2 picking up the hydrogen, becoming NH3, which is now the conjugate acid. Okay, so this is what we call a mechanism of a reaction, where you show the electron pushing going on. You will have to write all of this, so you might as well practice. So copy these and then write them on your own.